Oh, yes, please. Fiddle around with it.
So it's 12 minutes and then 3 minutes questions.
Let's admit it's again. I will try to be done.
I'll start with your 12 minutes.
So it should be okay, as long as I don't see suddenly just decide to make details. You know. You think, that. It was like when you teach. Of course, it's not mine. I'm only going to check out what I've done. To explain. Yeah. So but as I got to say, then you call it. Then if you can tell me another way to do this, I'll think about it.
Walker away. It's very soon.
You're backing.
Like to.
Somebody really coming.
Like to work on the markets. Working with
we have a meeting.
They didn't go out and party.
Yes. And University.
It's a pain in the ass, is what it is.
Hi. Hi, Malta. How are you? Long time to see you.
One thing that's it. Yeah, I mean, Judith is saying the same thing at best. They're down a number of posts and struggling to get people in.
All the class sizes have gone down. Although I was just in Canada for the GACMAC and talking to people at McGill. They were asking, what are your class sizes like? Oh, I was saying, yeah, ours are quite down. We're like, whatever, 15 people in third year. They said we have 2 in second year at McGill. This happened in the late 80s, early.
Oh, well, if something happens here, I can't read it. I need to find my glasses.
this way.
Side.
Aha. Marquez Woodrow, Hoden and Kruger. Good.
Hang on. It's a long day.
Yes, but actually, it's like the whole day. There's not so nice. Such. GIN. Oh. You know which one is working? So we are now going to start our session, to continue our session. And our next speaker is Sarah Jane Barnes.
Good afternoon. I'd like to talk to you about what the composition of chromites can tell us. Why would you want to do this? Well, as you all know, chromite is the source of chrome, and about 40% of it comes from massive chromite layers that are about 1 meter thick, and from mainly the Great Dyke, the Bushveld, and you could do it at Stillwater. And what we wonder is, what is the composition of the magma that forms these intrusions? Is there something special about them? And then given that the cotectic proportions of chromite to silicates is about 1 to 2%, does the current composition of chromites that we see reflect the initial composition? There's lots of other things we could address, which I've listed there, but we don't have time to do them today. If you want to talk to me about how to form a mass, what the chromite composition says about forming massive layers, that sort of thing, catch me at coffee and I'll bore you to tears. Right, so based on experimental work, the normal intensive variables, pressure, temperature, oxygen fugacity, composition of the liquid are all important. And if anyone wants to talk to somebody about this in detail, James Brennan, who's hanging around at the back somewhere, will talk to you about, there he is, does experimental work on this sort of thing, and he can talk, and he's got lots to say on that. Oxygen fugacity being one of the most important things, and composition of the liquid. And what we're after is composition of the liquid, if we can. But chromite tends to start crystallizing maybe 1500, 1400, and the system doesn't solidify to 1000 degrees. So re-equilibration is extremely common. And here we have an example of a chromite grain in the Emishan basalts, which is in the matrix. There's also chromites included in olivine. And that's the outline of the chromite. And then there's been overgrowth of iron-rich oxide. And these are element maps of all the different trace elements that we can do. And what you generally see is, of course, the overgrowth, the magnetite, or the thing that's tending to magnetite, it's not magnetite yet, is more iron, obviously. Cobalt is richer in almost everything except magnesium. It's poorer in magnesium. And so we have to take into account subsolidus effects if we're looking at the composition of chromites. So how am I going to do this? First, I'm going to look at the composition of chromites from komatiites of the Alexo in Canada and the Emishan chromites from China. Why do I want to do that? Well, these are volcanic chromites and there's rapid chilling, so that limits our re-equilibration, we hope. There's a range of liquid compositions in the case of the komatiites. It's just one locality, but there's two flows, olivine spinifex and clinopyroxene spinifex flows. So we can get a range of compositions. And at Emishan, we have the high titanium picrites and the low titanium picrites. So it's a way of testing whether the chromites actually reflect the liquids present. The metamorphic grade is lower green schist or less in the case of the komatiite, and Emishan is not metamorphosed. So hopefully we can forget about metamorphic effects. We'll look at the layered intrusions very rapidly. Great Dyke Bushveld are not metamorphosed, Stillwater lower green schist, so metamorphic effects should be limited. And we're going to compare the compositions of the massive chromite layers rather than the disseminated ones to avoid any subsolidus problems. So here is a comparison of the composition of the chromites from the, this is a classic, so try again. This is a classical chrome number, iron number plot that chromite people use all the time. These are the compositions of the olivine spinifex flow and the clinopyroxene one in blue. What I'm doing here is comparing the composition calculated by melts with the actual compositions. To use the starting liquid, I used the hyaloclastic breccia at the top. So there's no chromite in it. So I know what the real chrome content is. Because if you take a volcanic rock, there's often a few microchromite phenocrysts, and then you get a chrome nut. You're starting with a chrome concentration that's too high. So by using the glass, we hope we started in the right place. And I'm using oxygen fugacity at FMQ. That was calculated based on the vanadium content of the chromites. It comes out at about -0.4 to 0. So I'm just going to showing you the results for 0. So the chrome number tells us that these chromites equilibrated between 50 and 57 for the olivine spinifex, and we're getting down to 1400 for the Kleiner pyroxene spinifex. But the iron number tells us a different story. It wants the temperature to be about 1237 to 1157. Now, those of you who were, and that's the result for spin mills, for those of you who like spin mills instead. Now, for those of you who work on chromites regularly, this is really no surprise. It's well known amongst the chromite community that the +2 ions re-equilibrate. Now, because we know the iron and magnesium are exchanging, equilibrating, you immediately say, all right, do the other +2 ions do? So here, what I've done here is I plotted manganese in the chromite from the matrix and manganese that's from chromites in the inclusions at Emerson. The idea being the inclusions are more shielded than the matrix ones. And if there's no change in composition, you would plot on the one-to-one line. But what we see is generally the matrix chromites are enriched in manganese, which goes with the fact that we're enriched in iron, and the same thing for zinc. Magnesium is depleted. Cobalt and nickel don't change too much, but considering we put the chromite inside some olivine, probably that's having a role to play as well. But the +3 and +4 ions helpfully behave themselves. So if we look at titanium in the inclusion, titanium in the matrix, we're on a one-to-one line. Same for vanadium and gallium, and we can go through hafnium, tin, et cetera, et cetera. So the +3 and +4, we don't seem to see re-equilibration. +2, yes, we see re-equilibration. When we come to the komatiite, we can play even more sophisticated games because it's one locality. So if we take our initial magma, the breccia, and we are using melts with the conditions I gave you, we can calculate what the composition of the chromite should be. And that's the little round dots. And then that's the actual data. Now for titanium, melts gives you an answer because it calculates the titanium for you. For the other elements I'm showing you here, you certainly got your chrome number, but you have to calculate what the vanadium, gallium, and scandium concentration should be by assuming a partition coefficient for the chrome. And I've put up the ones I've got there, which are taken from the literature and pretty standard. Anyway, the main point here is the trace elements follow the fractionation sequence. The liquids appear, the chromite appears to reflect the composition of the liquid, even though we've only got 1 to 2% chromite present. On the other hand, when we come to the +2 ions, if you plot your +2 ions versus chrome number, it doesn't work. And that's not a surprise because the +2 ions probably diffusing the same way as the iron. So you're better off plotting them versus the iron number. And then you do see that generally as the iron number goes up, these go up. They're going along with the fractionation, but they're recording a lower temperature process. It's happening, they're re-equilibrating down to about 1100. The other thing we do here is we're comparing composition of titanium in the chromite, titanium in the whole rock for the Emerson basalts. And here you can see the high titanium chromites are richer, and high titanium chromite from the high titanium basalts is richer, and it follows the titanium of the whole rock. The same for hafnium, gallium. So in general, I'm happy with the +3 and +4 ions. From that, I designed a spidergram. So the spidergram is plotted in order of bulk partition coefficient into a cumulate that's consisting of 98% olivine and 2% chromite, which is roughly what you would have at the initial crystallization of things. So down here, that's the bulk partition coefficient, hence the order we've got. And what's nice about this is then you get all the +2 ions, which might get re-equilibrated at one end, and the +3 and +4 ions up this end. So the ones that are behaving themselves should be all together, and the ones that might be giving a different signal should be at this end. And I've normalized them to the chromite from the most primitive chromite we have from our Alexo flow. So the idea of being with the chromite has, it's an aluminium undepleted chromite, slightly light rare earth depleted. So it's a bit like a morve in a way, but a very high degree of partial melting. So we expect that, we know the magma is pretty flat to start with. So the chromatites come out roughly flat, zinc misbehaves a bit. Okay. Then if we look at the low titanium picrites and the high titanium picrites, you can distinctly see the high titanium picrites are richer in hafnium and titanium. Patterns are flattish with some a bit of scandium re-equilibration because there's a little bit of pyroxene coming in. And that is an important point. Scandium is controlled by pyroxene. So when pyroxene starts to crystallize, you start getting negative anomalies. So here's the Great Dyke. And at the Great Dyke, at the bottom, the chromite is in the dunite succession. So the only competing phase for the elements is olivine. So when you look at the Great Dyke, you get flattish patterns close to chromatitic, which is good because the model for the Great Dyke is a slightly contaminated chromatiite. And the contamination, the crustal contamination, that's why I put tin and hafnium on here in the first place, is showing up with enrichment of tin and a bit of hafnium. Okay, almost done, honest. And I put a bononite on here as well because sometimes bononites are proposed as magmas here, but we're nowhere near bononite in composition in some ways. And I better get a move on. Here is Stillwater. Stillwater is very tight. All the chromites are very in the same sort of spot. Notice the big negative anomaly here, and that's because there's olivine and pyroxene in the chromite layers at Stillwater. So the pyroxene is taking the scandium out. Bushveld, I'm only showing you the lower critical zone, as we could go on forever if we start on the upper critical zone and UG2. Again, we're flattish, but we're much more evolved than the other two that we looked at. I think it's because it is a contaminated chromatiite, but there's a lot more contamination in the case of the Bushveld than there is at the Great Dyke. And I just put the sills on where there's only 1 to 2% chromite present, so there may be some re-equilibration. But again, you can see the effect of the orthopyroxene here. And for those of you who like Kanametsky's diagrams, we're going to stop now. I added the chromatiite field to here, and the chromites, the Great Dyke ones are over here. The chromatites are indeed in the right field. There's up where the picrites, and that's where Stillwater and Bushveld are. And I have to stop because time's over.
One question?
Stunned silence. Either you didn't believe me or you don't know what I'm talking about, or I spoke too fast.
Well, let's then move quickly on the next talker, and we can talk with Sarah for next week. Great. The next talker is Juliana Marquez. Marquez, yes, please. You leave the clock.